Welcome to the Consulting Specifying Engineer webcast, evaluating and selecting generator set fuel sources, sponsored by Cummins. I'm your moderator, Amara Rasgus, and I'm happy to be here on behalf of Consulting Specifying Engineer and CFE Media and Technology. Here are some tips to help you get the best from today's webcast. If you're experiencing issues with your slides or the audio, please refresh your browser or click on the Refresh Media button directly under the presenter's photo. You can control the volume of this webcast by adjusting the volume on your own computer or by adjusting the volume on the webcast interface. If you have technical problems with the audio or with the slide, click on the question mark at the top right corner of your screen to access a list of system checks to try before contacting an online technician. But if you do need tech help, type a message in the Ask a Question box and someone will get to you as quickly as possible. Questions about this interface will be answered in the Answered Questions box. Please type your questions for our speaker in the Ask a Question box on the left side of your screen. The Q&A session will begin after the prepared presentation. Today's webcast is being recorded, and you'll receive an email within a week to a link with the on-demand event. To download a certificate of completion and a PDF copy of this presentation, click the Event Resources tab on the top left side of your screen. These documents will also be available with the on-demand version of the webcast. All right, well, I'm excited to introduce today's presenters. First, Mark Taylor is a technical advisor on Cummins North America products and services team, and he focuses on technical education and topics important to the power generation industry. Mark has served in roles that provide application engineering support for all Cummins power generation products in the North American market, including a leadership role serving the North American Sales Application Engineering team. Mark started his career with Cummins designing generators set subsystems, including cooling systems, air intake, and crankcase ventilation strategies. Scott Thomas will also be joining us for the live Q&A near the end of the hour. Scott is the Director of Sales Application Engineering in the Southern United States, and he's based out of Dallas. He leads a talented team of sales application engineers who spend their days supporting the questions and challenges designers and specifying engineers face every day. Scott brings with him 26 years of experience with Cummins and has served in numerous sales leadership and sales engineering roles. Thanks for joining us today. Mark, let's get started.
All right, thank you so much, Amara. First, before I get into the technical content that we have here today, I want to share with you that we'll be covering a fair bit of code language and requirements. We'll be leaning on NFPA 110, the EPA, CSA for Canada, and the NEC. We at Cummins work with these organizations on a frequent basis, so we feel we can offer a good faith insight and guidance for you during this presentation. That being said, we do not represent these organizations in an official capacity, and we urge you to consult the full text or your local authority having jurisdiction for any formal interpretations. If you happen to have any challenges with your local AHJ, we are happy to be your partner and to help you out. For today's course, we will be discussing how to specify gaseous generator sets. We will touch on key features and capabilities, as well as some installation considerations. The objectives of this course will be to contextualize gaseous generator sets for standby applications, comparing and contrasting with their diesel-fueled counterparts along the way. We will also review and dispel some myths and sometimes challenge the selection of gaseous generator sets, and provide some helpful specification language that drives appropriate performance-based requirements. As a consulting and specifying engineer, we do acknowledge that at times the decision on fuel source can be out of your hands, whether that be local requirements or a firm customer preference. We'll be sure to cover content that covers both diesel and gas, and best prepares you to respond to if there is any flexibility on the customer side with regard to fuel options. So you're best prepared to have those conversations. So I'm going to kick things off with you with an open-ended rhetorical question. You don't need to engage the chat or anything, but just answer this for yourself. When comparing a gaseous fuel generator set with a diesel generator set, what are some of the common differentiators between the two outside of, well, the obvious, the storage of diesel fuel versus the actual gas train that comes into a gas generator set? What comes to mind besides that? I'm willing to bet that some of you right on the onset are thinking costs, maybe different maintenance routines, thinking about emissions. Some of you might be thinking about, well, I just do whatever the customer wants. So we asked this question in the registration, and I read through your answers, and they were really diverse and considerate of so many things. I believe we will cover a lot of these items that you mentioned in this presentation here today. First, let's get started with providing an overview of the fuels themselves. As I said, we'll be looking at some similarities and differences as we proceed through this presentation. Diesel is known to be a power-dense source of fuel. That power density is also quite constant. In the United States, it would be regulated by ASTM D975 as ultra-low sulfur number 2 diesel. There are diesel substitutes in the market, such as biodiesel, whether it is a blend or 100% biodiesel. There are also paraffinitic, renewable diesel fuels on the market as well. But for the purposes of this presentation, when I mention diesel, I'll primarily be speaking in terms of 100% petroleum-based diesel. On the other hand, gaseous fuels may not be as energy dense and may encounter more variability in energy content. Generally speaking, for the United States, the energy content of pipeline natural gas is quite reliable, but it is not immune to fluctuations or regional differences. Just like how I mentioned, I'll be discussing diesel in general terms. When discussing gas as a fuel for generator sets, I'll be primarily referring to pipeline natural gas. At a very high level, this hierarchy I have here shows the relative energy density of the fuels between liquid and gaseous fuels. For the space that they take up, diesel fuel has the highest energy density among these fuels. Historically, it has been perhaps too easy to draw a correlation between energy density and generator set performance, such as starting times and transient performance when taking on heavy loads, for example. But the advances in technology have been trending in a way that blurs the lines between these two notions. We'll get back to that point as we go through the performance requirements section of this presentation. This next table takes a deeper look at a variety of gaseous fuels, and you might even recognize a number here. But again, looking at energy content measured in BTUs this time, we'll start with pipeline natural gas on the high end of this list. Compared to other forms of fuel in the gaseous form, this will also very likely be the fuel used in standby applications. As you go down the list, many of these fuels may be a result of an industrial process or treatment. These fuels at times are consumed on site with a generator set designed for efficient continuous duty, or that fuel might be exported and cleaned and sold as a commodity. Compared to its peers, though, pipeline natural gas is generally high energy and freer of contaminants. That being said, natural gas cannot be assumed to be of a perfect standard composition. Gas constituents will vary by geographical area. Its composition can vary if it depends on for example, a single wellhead that might be aging, as opposed to a network that draws from multiple sources. Though pipeline natural gas is generally quite reliable in the United States, it never hurts to conduct a fuel analysis to be sure of the energy content if there is ever any doubt. Cummins will be glad to assist in interpreting the results of a fuel analysis with you. Recall, a reciprocating internal combustion engine is converting the chemical energy of a fuel into mechanical energy by capturing the force of combustion in the cylinder of the engine. Ideally, the spark plug is providing that initial flame that drives that combustion. That brings us to one of the most important means of describing a gaseous fuel, which is done by methane index number. This value describes how likely a fuel is to combust uncontrollably, creating knock or pinging in an engine. On a scale of 1 to 100, a methane index number that is higher may be less likely to lead to engine knock, where a lower value may be more likely to provide issues with engine performance. Correlating this into practical terms, a lower methane index number may mean a gaseous fuel generator set may incur a power derate. This table that I have shown here is an example from one of our own products. Let's say if the methane index number cannot exceed 57 per a fuel analysis, the on-site fuel is measured to be 57 methane. We'll be looking at a max available power of 75% of the nameplate rating of the generator set to achieve best performance. Generally speaking, a fuel analysis of pipeline natural gas will produce a nice and high methane index number, usually around 80 or even 90. And in the graphic on the right, this seeks to show just kind of how the methane index number for pipeline natural gas compares to some other common fuels. So let's connect the dots between my first spec recommendation I provided earlier about seeking out the fuel's methane number with a fuel analysis, and whenever there's any doubt to its quality, and knowing the properties of the methane index number of a fuel, one should be able to draw a straight line from that value to a generator set manufacturer's data sheet in order to make sure that that product is able to run optimally. This confirmation should be an expectation on the manufacturer's data sheets. So it's up for us to make that available for you. And for us, we offer that right on page 1 of our gaseous fuel generator sets. It's not hiding anywhere. The next subject I'm going to cover are 2 terms you may or may not be familiar with, and that's rich burn and lean burn. Generator set manufacturers may commonly refer to their products with these terms, and at the end of the day, I want you to recognize the meaning behind them, but I also want you to be assured that both may be suitable for your application. The key characteristic that are usually cited when explaining the differences between rich burn and lean burn are the air to fuel ratio, the typical oxygen content in the exhaust air, the typical applications they can be found, and lastly, the general expectations for emissions performance. Rich burn engines are generally associated with fast starts, being able to handle larger block loads, very close in performance actually to their diesel counterparts. They may be known for needing some form of aftertreatment due to their emissions constituents. We'll discuss emissions a little bit later in this presentation. Lean burn engine-driven generator sets, in turn, are generally associated with high efficiency, continuous duty applications. They also can often meet emissions requirements without the use of any aftertreatment. The terms rich burn and lean burn generally are pointing to the air-fuel ratios and amounts of excess oxygen in the exhaust. These traits and characteristics are good to know for me as an engineer working for a manufacturer that happens to make engines. But for you as a specifying engineer, what should really matter at the end of the day is the performance of these engines. Investments in engine technology continue to advance. And as such, the lines that divide these 2 columns in reality are getting more and more blurred more than ever. There are lean burn generator sets that provide rapid response times and load acceptance that make them a valid standby option. There are also peak shaving and continuous applications out there where a rich burn generator set is best suited for the job. So with that said, I'd like to challenge everyone when specifying gaseous fuel generator set to keep a performance-based mindset and avoid outright specifying terms such as rich burn and lean burn. Stick to the project requirements such as transient performance, emissions limits, start time, without citing which fueling or engine technology. That way, you will keep the broadest range of possibilities available to fit your needs. So that wraps up the portions of today's course covering just the basics of fuel, whether it's diesel or natural gas. I'm now going to check in with you all to see if you've been following along. with our first concept check of the day here. So question, when describing gaseous fuels, which of the following attributes are often used to describe fuel composition? So this is a select one answer. Here we go. I'm starting to see the results come in. These are some, I think people are tracking along here. I like what I see here. That means you all have been paying attention. I think basically, overwhelmingly, I'm seeing everyone say, hey, methane number. So great, absolutely. And I saw a couple people for the other answers, just to recall, ASTM D975, that's a diesel standard. Air fuel ratio, that's something that, that's kind of what we worry about as engine and genset manufacturers. So yes, thank you all for engaging with that chat, with that survey. We will have a couple more along the way here as we go. So I'm going to kick off this next section with a myth that generator sets, that gaseous fuel generator sets may not be suitable for emergency or life safety applications. By the time I'm through with this section, we'll review this myth to see if it holds water. So let's begin by looking at how codes and standards regard generator sets powered by both fuel types. One of the leading concerns for gaseous fuel generator sets centers around the applicability of such a fuel for emergency standby systems. In the eyes of NFPA 110, and this is a snippet from the 2019 version here, the emergency power supply, that's the generator set itself, can be permitted to be fueled by liquid fuel, liquefied petroleum gas, which is commonly seen propane, or of course, natural or synthetic gas. So just to be clear, a gaseous fuel generator set is okay in the eyes of NFPA 110 in this section here. NFPA 110 also contains requirements pertaining to on-site storage of said fuel sources, and I'll be spending the next handful of slides on this point. The first thing I'll mention is that NFPA 110 does indicate that where applicable, level 1 emergency power systems, power supply systems may be fueled primarily from a natural gas utility source. This is to acknowledge that for many parts of the United States, the natural gas infrastructure is very reliable, to the point where the gas line can be the sole source of fuel. However, this exception text below cites that in locations where the probability of interruption of that off-site fuel source is high, on-site storage of an energy source sufficient to allow for the full output of the EPSS to be delivered to the specified class in hours shall be provided. So the key operative word here is high. A high probability of gas utility interruption will drive the need for an on-site source of fuel. In some regions of the country, let's pick on California, for example, on-site storage is effectively a blanket requirement due to it being a seismically active part of the country. For many parts of the country, this discussion can be up to the local authority having jurisdiction and the local utility. To put this conversation that may occur between you and the AHJ and the local utility into context, the Natural Gas Council put out a study that worked to quantify how reliable the nation's natural gas utility really is. Due to natural gas infrastructure having such geographically dispersed production sources and the interconnected nature of the network, the U.S.'s natural gas network's reliability was quantified to be exceptionally high, robust enough to be considered a primary source of fuel for level 1 applications. Quickly switching gears here, having just covered NFPA 110 requirements, I would like to dedicate at least a slide to focus on the CSA language for our Canadian audience members. CSA282 is the counterpart to NFPA 110, and there are a lot of similarities here. Regarding on-site fuel storage, you'll notice callouts to 2 hours of runtime under the maximum site design load, and the requirements go further for healthcare facilities. For healthcare facilities that fall under CSA Z32, a fuel supply shall be maintained on site at all times for at least 24 hours for Class B and C facilities and at least 72 hours for Class A facilities. Similarly to the exception clause for NFPA 110, CSA282 also provides language to deem on-site fuel storage as not required if it can be demonstrated to the AHJ that fuel supply reliability is sound. So in short, there's a lot of parallels between CSA282 for Canada and NFPA 110 for the United States. So back to the United States. Let's take a look at this map of the United States just to highlight this point more visually. Again, the driver of such a reliable source of fuel is that the infrastructure network and production sites are geographically dispersed and well interconnected. So I realize that we just covered a lot of nuance and a lot of language and code language in a relatively short span of time. Thanks for sticking with me on that. I have this table here in an attempt to best summarize on-site fuel storage requirements, whether it's diesel or gaseous fuel. Looking at the rows, covering the different articles of the NEC and the columns for diesel, which is inherently an on-site fuel, gaseous fuels, whether it is utility only, and differentiating it from on-site storage. Of course, a gaseous generator set with on-site fuel will meet those requirements, same as diesel, so long as that storage is appropriately sized, of course. But to best summarize gaseous fuel generator sets with utility-only sources of fuel, NFPA 110 Level 1 systems must include on-site fuel storage, again, if the likelihood of the loss of the utility is high. Therefore, once again, I recommend that this drives a conversation with your local AHJ and local utility for what is that definition of high. I must also note, I'm making a general assumption here between Article 700, generally falling in line with NFPA 110 Level 1. Confirm that with your AHJ if there's ever any doubt. Finally, I'll note here that Article 708, Critical Operations Power Systems, does contain language that actually explicitly requires on-site fuel storage for combustion engine-driven generator sets. So there's no way out in that case. So in some scenarios, solely relying on the utility may be a more nuanced conversation with the AHJ. But those are conversations that happen frequently, and relying on the utility as the sole source of fuel can be very reliable as a means of fueling a generator set. Granted, I know that most of you have seen news stories or have personally experienced the challenges that can shake our confidence in our infrastructure. We're currently getting ourselves out of a gasoline pipeline mess throughout the Gulf and the East Coast following that ransomware attack. Just a few months ago, we experienced dire challenges in and around Texas with that terrible cold snap. The names Sandy and Katrina are also forever etched into memory for how those storms impacted New York and New Orleans. They both had natural gas issues compounded by old infrastructure. That being said, for the times where we can point to natural gas networks letting us down during extreme circumstances, there are other examples where the gas utility was holding strong when the diesel fuel infrastructure was challenged. How will a fuel truck deliver diesel with countless downed trees blocking the roads? How many other facilities are going to take priority over your building or facility when fuel is scarce? Evaluating the particular circumstances, design, and yes, risk factors is what engineering is all about. That's why exercising and documenting best engineering judgment on a case-by-case basis is so important. Each location and each situation are so different. We cannot make a claim that one source of fuel will always be better than the other. The next standard, shifting gears here, the next standard we're going to be covering is ISO 8528. I'm certain it is being called out in your generator set specifications, but usually specs do not go much further than calling out emergency standby power rating. I want to ensure that we level set the expectations of calling out an ISO rating. The first thing to reinforce is that these ratings do not include any fuel type requirements, so it's effectively blind to the selection of fuel used in the generator set, whether it is diesel or gaseous. Now, what does ISO 8528 cover is the definition of a standby rating. It is the expected duty cycle and usage. Standby generator sets are typically used to back up a primary source of power. So the expectation is that the number of hours of runtime is generally low and that the loads are variable. Guidance on load factor over time is also called out. ISO 8528 is a reference standard, and every reputable manufacturer of generator sets should be designing their products to at least meet these standards. So continue to call it out in your specifications. There's nothing wrong with that, but just let it be known that ISO 8528 standby does not exclude gas or diesel one way or the other. We discussed NFPA 110 earlier in this presentation, but you all know we can't go along without talking about it some more. This time, I'll be discussing NFPA 110's type of an emergency power supply system, or EPSS. Type is the maximum time in seconds that the EPSS will permit the load terminals of the transfer switch to be without acceptable electrical power. And just to reinforce this point, this requirement is not just for the generator set start time, and it's also not measuring from generator start all the way to every single load is back on and everything's fully functional all the way down to every receptacle, but is the time from power out to acceptable power at the load side of the transfer switch of the EPSS. Types can come in a variety of designations, but for life safety applications, you will most likely see requirements for type 10 for 10 seconds, and you may also have encountered requirements for 60 or 120 seconds for other types of loads. What you will not see here, however, is NFPA 110 calling out a fuel type for emergency power source in order to fit the requirements of one type or the other. So just like ISO 8528, it's just a performance-based standard. Of course, specify NFPA 110 type to fit the needs of your application and applicable codes and requirements. Do not let the start time requirements rule out a certain fuel type if both diesel and gaseous fuel generator sets can meet these requirements. So work with your generator set manufacturer for any help in understanding the options that you have available. Once again, I'd like to take a quick aside for our Canadian audience members. The counterparts to NFPA 110 and are CSA 282 and CSA Z32, like I mentioned earlier, and it adds further requirements for healthcare applications. One key distinction of CSA 282 is that for life safety equipment, 15 seconds is the time requirement for acceptable power to be provided on the load side of the transfer switch or power supply system. A 10-second requirement, however, does come into play for vital loads of essential electrical systems for healthcare per Z32. Other loads, such as those crucial for firefighting or healthcare delayed vital loads, they may be on a 1 or 2 minute requirement. The important note here is that these requirements do not exceed those by NFPA 110 type 10 for emergency power supply systems. And once again, these are performance requirements that are not specifying any fuel source. So with that, I hope you take away that the notion that gaseous fuel generator sets not being acceptable for standby applications is indeed a myth. Don't rule them out with a broad stroke. ISO 8528, NFPA 110 certainly do not. Base that decision on the individual performance of the product based on your performance-based specifications. We discussed that sometimes the AHJ and code requirements for on-site fuel storage may drive a more nuanced conversation on solely relying on natural gas utility as a primary source of fuel. Let a good understanding of the codes and proper hazard analysis guide you in those decisions. Have that conversation early with AHJs and bring in any help from your generator set manufacturer whenever you need it. As you know, NFPA 110 plays a massive role in emergency power performance and reliability requirements. We all discuss the standard in so many of our industry webinars, including our Cummins Power Hours. I provided links here for our most recent webinar where we cover more detail on the performance side of NFPA 110 if you're so interested. When you get a copy of this slide deck, you can click this link for more information. Moving on to our next myth that I would like to bust for you is the notion that gaseous generator sets are always cleaner than their diesel counterparts and that they never need exhaust after treatment. Granted, some myths and misconceptions may have some basis in fact, but this conversation is much more nuanced than this blanket assumption. So let's dive into those details. As this presentation's goal is to provide a comparison and contrast of fuel sources, I'll now go into some of the details on which emissions constituents the EPA new source performance standards regulate within the context of diesel and gaseous fueled engines. First is NOx, or oxides of nitrogen, and is regulated both for diesel and gaseous engines. If I were to ask anyone to name one emissions constituent from memory, NOx is likely to become first to come to mind. And this is because NOx encounters so many additional requirements, especially at the local level. I'll get to that in just a little bit. Next is hydrocarbons. They can come in many different types of molecular structure and also both regulated in diesel and gaseous engines. Next is particulate matter, and it can best be described as anything that creates visible soot or smog, or something more appropriately, if you put a filter at the exhaust, it would collect something, it would show up. This is something at the federal level is only regulated for diesel engines. Next is carbon monoxide, and again, regulated for both types of engines at the federal level. And lastly, oxides of sulfur are only for compression ignition engines. Just making sure I advance the slides here appropriately. Now that we've covered the emissions constituents, the other key part of the conversation is emissions requirements. First, we'll go into how gaseous and diesel fueled engines are identified and regulated at the federal level. In the United States, the federal level of requirements are set by the EPA's new source performance standards. Reciprocating internal combustion engines are then identified into two main categories: compression ignition and spark ignited. Diesel engines fall under compression ignition, as the heat of compression within the engine cylinder creates the combustion event. Gaseous engines fall under the spark ignited category. As the name self-describes, there is a spark to create the combustion event. The next round of categories that are important to understand within the context of the US EPA is that engine being used. Let's compare stationary and non-road first. Once again, self-explanatory. A stationary application is one that is permanently installed. Non-road indicates an engine that is mobile, but not is providing the propulsion of that vehicle. A trailered generator set is a great example of one of our products that would be regulated in this space. Between the two types of stationary applications, there are those that are intended for emergency use and non-emergency use. So put plainly, an emergency application is one where the engine-driven generator set is used as a backup to a primary source of reliable utility power. In turn, non-emergency comes into scope for applications where the engine is running to produce power when there otherwise was an acceptable utility power present. Now that I've covered the basic categories and terminology, let's dive into some of the nuances of emissions requirements and factory certification. For diesel-fueled engines, as well as rich-burn propane engines, it is incumbent on the engine manufacturer to factory certify their products. That's going through the required testing and reporting with the EPA for families of engines used in generator sets. For other engines, such as natural gas engines and lean burn propane engines, factory certification is optional. So what does that mean for you? For starters, this is not necessarily a bad thing at all, but what it may mean is that it is important to know the engine's certification status, as that may drive that the end user or operator may be responsible for demonstrating compliance by following this tiered guidance I have shown. Referring to this chart, the requirements for an owner or operator can be as basic as simply maintaining appropriate records on the engine's maintenance for relatively small products. For slightly larger products, the scope increases to initial performance testing within a year of engine startup. And for engines greater than 500 horsepower, the scope of work expands to include subsequent performance testing every 8,760 hours of runtime, or 3 years, whichever comes first. So in keeping with a common theme here, lean on the generator set manufacturer to provide appropriate documentation demonstrating compliance with specific emissions levels or engine certification. Have them be clear if the product is factory certified or not. Switching gears quickly here, just once more, I'd also like to cover the Canadian equivalent of the slide I just had up. This is a snippet of information, just only a snippet of information. I know there's plenty of information for both the US and the Canadian standards. But there is a fair amount of harmony between the US's EPA and Canada's MSAPR, but some key differences still exist. For example, the horsepower thresholds from the last slide of 100 and 500 engine horsepower for the EPA is basically in line with Canada at 75 and 375 kilowatt once you do the conversion to metric. However, distinctions are made between a regular use engine and a low use engine, and the emergency standby space engines will typically be considered low use. There are also distinctions between modern engines and pre-existing engines, but for reference, I'm only showing data for modern engines. Pre-existing engines have generally the same requirements, but are typically more generous in allowed NOx, and the intensities are a little bit less inclusive in their ranges. But please reach out to your local Cummins sales person if you have any questions about your local needs. So bringing the slide back to your attention, where we sought to identify the types and usage categories for the federal level with the EPA New Source Performance Standards. The federal level establishes a baseline level requirements, but any local air board can exceed those requirements. It is tough to fit local air requirements into nicely named categories like the EPA's regulations, but simply just be aware that local air boards have the authority to regulate each emissions constituent above and beyond the EPA's limits. They can pick one or multiples of the different emissions constituents as we discussed earlier. Furthermore, just because a certain emissions constituent is not regulated in the EPA space doesn't mean a local requirement will not exist for it. For example, there might be areas of the country where for spark-ignited engines, as you recall, that was not regulated for particulate matter, but the local regulation might have a stipulation on particulate matter for a spark-ignited engine. As I mentioned before, the generator set manufacturer should be your partner in this process when it comes to precisely understanding their products. Require the manufacturer to provide appropriate documentation demonstrating compliance within the acceptable limits of the US EPA, whether it's stationary, non-stationary, or whether it's emergency or non-emergency. This is also the case with specific emissions levels requirements as well at the local level. So far, I've covered the major emissions constituents that are present and different exhaust streams from diesel or gaseous fuel generators and at the federal and local requirements around them. At times, it may be necessary for a generator set to include one or more after-treatment technologies to meet these requirements. Particulate filters may do as their name describes, reduce particulates, and there's a whole slew of different technologies and bolt-on attachments, basically, for lack of a better term, that would reduce different constituents. But that all said, avoid specifying specific emissions technology, as that may over-constrain an otherwise well-constructed generator set specification. The selection of technology is a key output response from us to a specification that indicates usage and duty cycle, as well as the emissions requirements from federal, state, local codes. So always reach out to the manufacturer early if there are any questions on these issues. So I hope I've effectively debunked this myth that started this whole conversation. Emissions requirements can vary by usage and by local jurisdictions. There are even regions in the country that may effectively push what an emergency use generator to have technology that is at tier 4 levels, for example. So applying a blanket statement on one product or technology over the other, especially when the local requirements are so variable, isn't in anyone's best interests. So if you're interested in diving even deeper into emissions requirements and constituents, I have referenced here some excellent resources as well, and you'll be able to click these links when you have a copy of the presentation if you'd like to learn more. So this is another opportunity to check in with you all to see how well you're doing. I have another concept check for you. So when specifying a generator set solution for an emergency power system, make sure to include, and in this case, this is a select all that applies, so you can select more than one. Checking out the refresh rate. The very first respondent nailed it 100%. Here we go. Now they're flooding in. That's great. No, you all are very well tracking along here. You guys are experts. I would say that I'm ready to move on since I've already seen that you guys are basically in alignment. Yeah, A, B, and C. Those are the three main hitters. So I'll go ahead and keep moving forward here. So here's the fun part where I have more pictures of generator sets. Installation considerations. So in the last series of slides I have for you today, I'd like to go over key installation considerations for gaseous and diesel generator sets. First, I would like to acknowledge the numerous items that are actually the same, at least very similar between the two different kinds of generator sets. Both are powered by a reciprocating internal combustion engine and such produce vibrations that may need to be accommodated with proper mounting, such as a proper foundation or anti-vibration mounts when necessary. Exhaust system routing designs for both generator sets are also no different. Key concerns being the proper routing, muffler sizing, termination, routing through walls appropriately, cooling system design and sizing as well. Having proper airflow, proper cooling, it's not really any different. The starting systems, especially the batteries, those are the same. Remote monitoring systems, connections, controls, you name it. There's plenty that are similar between the two fuel types. So that all said, there are a lot of similarities for the application and design considerations of gaseous and diesel fuel generators. We don't have, obviously, enough time to cover all of these in more detail, so I will park this link for you here. It's our T030 application manual, and it is a manual. It's a book. It's a great resource that is brand agnostic and fuel type agnostic. It provides all sorts of guidance for designing in and around a generator set. I highly recommend downloading it. It's free and available for you. Like I mentioned, that list of application similarities between diesel and gaseous generator sets is quite long, so we'll be covering the things that are actually different between the two. First and most obvious is that diesel drives the need to store and maintain fuel on site, right? As we mentioned earlier, code requirements will drive the NFPA 110 class, which in turn drives the size of the on-site storage. The more fuel that is present, the more fuel that needs to be maintained. Fuel does not stay perfect forever. Above ground tanks are open to the atmosphere and they need to breathe. A breathable tank not only allows for filling and fuel consumption, but also the accommodation of seasonal and daily temperature fluctuations. Due to the inherent design characteristics of tanks being open and exposed to air, it's unavoidable for tanks of this design to prevent the eventual ingress of water, which could lead to water and fuel and even microbial growth within the fuel. And microbes, when they get sucked in by the fuel pump, they clog up a fuel filter. That could be a down gen set. For standby applications, it is not required, but we do recommend minimizing the amount of biodiesel used to store in on-site fuel tanks. This is not a comment on whether or not engines can handle biodiesel. It's purely coming from a storage standpoint. Biodiesel blends may result in the need for shorter maintenance intervals, as they are more susceptible to spoiling with that water ingress that I mentioned. So the key takeaway here is to not assume that on-site stores of diesel fuel will stay perfect forever. NFPA 110 calls for annual testing of the fuel. And if the fuel is of substandard quality, it needs to be polished or potentially replaced. Another key tip, don't put off getting that service started. Establishing an early baseline result during commissioning is the best point of comparison for future test results. Compared to on-site storage requirements of diesel, gaseous fueled generator sets can potentially be much easier. As we mentioned earlier, if an installation can solely rely on the gas utility as the sole source of supply, then it doesn't have to be concerned at all with the items that we cited. If on-site storage of gaseous fuel is needed, for example, propane, that fuel does not go bad, and it is sealed from the environment under pressure. Its shelf life is basically limited to the life of the tank. That all said, this is not to say that gaseous fueled generator sets are without nuance. Generally speaking, a diesel generator set is fine, so long as the fuel tank is close in proximity and full of fuel, of course. For a gaseous generator set, the key watch out is ensuring the gas supply can provide an adequate pressure and volume of fuel. Appropriate sizing of fuel lines needs to be done, factoring in all sorts of restrictions to flow, such as long runs of pipe and elbows. Ensure that the gaseous generator set is fueled by a dedicated gas line. That serves two roles: to isolate the generator set from potential pressure and flow fluctuations from other parts of the facility, and also in the event of an emergency, to allow the firefighters to maintain fuel flow to the generators when they need to shut off the gas lines for everything else in the building. Again, it is important to that the supply can provide enough volume and pressure of fuel at the rated load of the generator set. That last part is an important distinction, as a seemingly okay pressure reading when the fuel is not flowing does not mean that it'll be appropriate at full fuel consumption. To mitigate these challenges, at times installations may need for accommodations such as accumulators or compressors to boost the supply pressure. Of course, the minimum requirements for pressure and flow should be readily available from the manufacturer in their data sheets, and that should be an expectation on your side, and that should be available. One other key differentiator I'll cover are the operating costs of generator sets fueled by diesel or natural gas. Generally speaking, kilowatt to kilowatt, when it comes to the initial capital expense to purchase and install a generator set, diesel tends to be the cheaper option, of course. A lot of that driven by just how power dense the fuel is. You can get more power out of the smaller engine. Over the long term, however, due to increased costs of procuring and maintaining diesel fuel, that edge does tend to erode. That is one reason why when it comes to the non-emergency space for demand response or peaking or continuous duty, that's why it's gaseous fuels that are so often used. They're quite popular for that purpose. So if you're working with a customer that is open-minded to the possibility of both diesel and gaseous fueled generator sets for their next project, present the value proposition in terms of near-term versus long-term costs, as well as the convenience of not having to maintain diesel could possibly offer. I'd like to wrap up with one last myth that I would like to bust, and that is the notion that gaseous generator sets are always worse than diesel-fueled generator sets when it comes to transient load response. Engine and fueling technology have definitely been blurring the lines between engine performance of both fuel types to the point where there is parity between them for a wide range of kilowatts. Further, this is a great opportunity to highlight that performance against 100% rated load acceptance may be an interesting basis of comparison on paper, but not nearly as practical a comparison between products based on the actual required load performance of that application. The best way to evaluate how a generator set may perform against the loads and load sequencing in your design is to run it against the product sizing software. I also challenge you to evaluate both diesel and gaseous fueled options, not ruling out one from the onset. If you have any notions that diesel is always better than gaseous fueled generator sets, I'm sure you'll be delightfully surprised to see how capable they are if you gave them a shot. So regardless of fuel choice, running the facility loads against a sizing software, such as Cummins' its GenSize, is the most robust approach to finding the best fit generator set for the application. Now, just because I'm super interested in getting feedback from you all in the Q&A, for the interest of time, I'm going to skip this concept check here for you now. But just so you know, when considering a natural gas generator set, of one of these that is not a key installation, an operational item to that is not a differentiator, and that's going to be C, foundation, mounting, and vibration. But I'm really excited to get to the Q&A, so I'm going to skip this one and move forward. With that, I'll sum up by saying that between diesel and gaseous fueled generator sets, there is a lot of parity between the two engine technologies. Natural gas can be very reliable as a source of fuel, even when sourced from the utility only. Emissions-wise, there are some key differences, but generally, the approach to meeting local and federal requirements are quite similar. on-demand response or continuous operation generator sets are excellent choice to consider, not only because of emissions, but also for its efficiency and fuel costs. In the standby space, I hope you come away empowered knowing that many of these products can meet the strict transient performance requirements and start time requirements that are not only just for diesel-fueled generator sets. So at the end of the day, if you have a customer that is open to generator sets of either fuel type, I hope you feel empowered to have a constructive conversation on the merits of both. Further, I hope you know that there is a network of resources and available individuals that are very helpful and ready to support you in these conversations. Speaking of resources, I know I covered a lot of ground here today, and I linked several resources throughout the presentation. Here, I more or less compiled an index of those cited works for your ease of referencing later. These links are clickable once you get a copy of the presentation. And lastly, if you enjoyed this content and wish to be notified by Cummins of our series of webinars or our white paper subscriptions, I encourage you to subscribe by clicking on these links that are available for you here. We do make more than generator sets, after all, so we cover all things from system level controls to our brand new series of transfer switches. And so if you're interested in learning about the rest of the power system, we're here to help as well. So with that, I'm going to toss it back to Amara.
Awesome. Thank you, Mark. I appreciate that information. So Mark's going to stick around with us, and Scott will now be joining us to answer questions. Please type your question for the presenter in the Ask a Question box on your screen, and we'll get to as many as time allows. Questions that we do not get to today will be posted online at www.csemag.com with the archived version of this webcast. And as Mark alluded to download a certificate of completion or a copy of this presentation with all the links, please use the Event Resources tab on the left side of your screen. All right, gentlemen, we have a lot of questions, so I'm going to get started here. Scott, this first one goes to you. Can natural gas generators meet code requirements for standby service?
Thanks, Amara. This is a very common question that we get in the field. The short answer, and I think Mark covered this very well in the presentation, is yes, natural gas generators can be used in legally required applications. If you're considering using a natural gas generator in a legally required application, there's three things I would check on. Is number one, the manufacturers that you've got listed in your specification, verify that those manufacturers can meet the 10-second start requirement. Number two, check with the gas service provider and validate that the service is reliable. As Mark mentioned during the presentation, in most cases that is true, but we've run into pockets of area where the natural gas service has been somewhat questionable. And then lastly, and most importantly, check with the AHJ. Ultimately, we have to get their approval as a project team if we're going to apply a natural gas generator into a legally required application. So that's the last step.
Got it. Thank you, Scott. All right, Mark, this next question is yours. Let's talk about wet stacking. Does that happen in diesel generators only or natural gas too?
Yeah. Man, how on earth did I talk so long and not talk about wet stacking? Oh man! So, wet stacking, yes. For those of you who don't know or what we're talking about with wet stacking, that's a phenomena basically of a lightly loaded engine getting exercised frequently at practically no load or no load at all, and unburned fuel, not being burned, tends to go out the exhaust and create problems for the engine. Engines like running hot; they like running at load. And so prolonged exercising at low loads can result in wet stacking, carbon buildup, unburnt fuel. The short answer is that worry, it does not exist for natural gas engines in their generator sets. The Spark does a really good job of ensuring that combustion happens. With a cold diesel engine, it requires on a hot cylinder to create the combustion event, which results in the unburned fuel. But with natural gas, that spark plug The fact that they run a little bit hotter, the fact that the fuel is a little bit cleaner in terms of, it's a gaseous fuel as opposed to a liquid fuel that has other additives in it. That all leads to basically the short answer of it's not nearly as much a concern to lightly load a genset that's gaseous fueled. But to that point, always refer to the manufacturer's recommendations for how much you should be exercising that generator set, whether it's diesel or gas.
Sure. Got it. Okay. Scott, I'm going to send this next question over to you. Do you have any advice on the use of biofuels or vegetable oil as a biofuel?
This is another question we're getting more recently, actually, in the field. I think Mark did a good job of covering this in the presentation as well. When you look at it from a Cummins perspective, most of our engines, diesel engines, can run up to a 10 to 20% blend of biodiesel and traditional diesel. If you're working on a project that is a standby generator, where normally it's going to run a maximum of 50 hours per year once we figure out the testing and the actual outage time from the utility, the problem with applying biodiesel is it degrades very quickly in the fuel tanks. So when we see issues in the field, it's normally associated with, number one, the starch system, but also the fuel system. We see that fuel degrade, and when the generator is called to run, the filters get clogged, and ultimately it can create a shutdown at the generator and impact its reliability. So the answer is yes, we can run on biodiesel and other fuel blends, but they can degrade very quickly, so that's something we have to keep in mind. So for standby applications, we generally recommend just stick with the standard ultra-low sulfur diesel for those type of projects.
All right, good to know. Mark, I have a question for you. It's a multi-part question, and I can go back to any of this if you need me to. How can you derive optimum fuel consumption from your generator? That's the first part. Then, does the life of a generator get affected when operating on its full capacity? And if so, what is the cost comparison in relation to fuel consumption when operating at 75%?
Awesome. That's a really cool question because it kind of reminds me of hypermilers or people who are trying to run as effectively or as efficiently as possible. I would say, first off, the most important thing to mention is the rating of a generator set. Let's call it a 1 megawatt, 1,000 kilowatt product. Generally speaking, the sizing of a product to accommodate cyclical loads, to accommodate motor starting, that's part of the reason why there's a general recommendation that you size a product so that 70 to 80% of the nameplate rating is where you're generally at for your loads, just to accommodate the cycles and as things come and go. You need a little bit of breathing room on that engine and that generator set. With regard to the question of fuel efficiency, you probably think about this in terms of your own car. There's like an optimal RPM to hit for cruising. Low RPM at your top gear is usually really efficient. It turns out for our generator sets, we're already operating at a very efficient RPM. 1800 RPM is a sweet spot, for diesel and gas. And so at that point in time, your rating scales actually quite linearly with power. And so if you're running at 70% of nameplate road, you're probably going to be burning 70% of the gas. And so you're not going to get any efficiency gains one way or the other that way.
Cool. Well, we have time for just one more question. Scott, if you could take this one on in the next minute, I'd appreciate it. How do you manage fuel quality issues with ultra low sulfur diesel, or ULSD?
This ties really well into the previous question I answered. Is it's critical for us to validate that the fuel quality in the fuel tank supporting the diesel generator is going to stay in the shape that we need to stay it in. The best way to do that is test it frequently. Work with the local fuel service provider, get it tested on a quarterly or twice a year basis, validate that it's in good shape. If it's not, then that fuel service provider can work with you on a plan to basically get the fuel where it needs to be. And that may be a simple treatment plan. It may be bringing out a fuel polishing system to clean up the fuel. If it degrades too much, it may be a complete fuel replacement, but test the fuel frequently to verify it's in the shape that we need it to be reliable.
Okay, well, thank you. And thank you for all of those great questions. Our terrific speakers today were Mark Taylor and Scott Thomas. I appreciate you sharing your time and expertise. I'd also like to extend a special thank you to our sponsor, Cummins, for sponsoring today's event. And now that we're just about done, we want to hear about how we did. An exit survey will pop up on your screen as soon as this webcast ends. Please take a moment to complete it because we do use it for future webcasts and to improve our events. Finally, on behalf of Consulting, Specifying Engineer, and CFE Media and Technology, I'd like to thank you for attending. This now concludes our webcast. Thank you and goodbye.